Hey there. In this video, we're going to talk about integrating in spherical coordinates. And here's a problem that we'll be looking at. We want to integrate this function over the region between the sphere of radius 3 and the cone of rays from the origin at an angle of 45 degrees from the positive z-axis. So what we see here on the top here is the sphere of radius 3, and then over here, down here, we have the cone of rays. We have a ray is just a line, it's half of a line. It's a line that starts at a point and goes out in one direction. So they're starting at the origin and they're shooting out forever in some direction. And that we're instructed that that's exactly 45 degrees from the z-axis. And if you look at the region between that cone of rays and that sphere, we have this shape over here. And just to give you a better idea of what that looks like, I've got it in 3D over here, and you can see the cone at the bottom, and we have the spherical cap at the top. And we want to integrate this function over that region. Well, that region is comprised of a sphere, a spherical piece, so it might make sense to try to use coordinates that are adapted to something spherical, and that's where spherical coordinates are going to come in handy. So let's take a look at how we're going to use spherical coordinates to integrate, and then we'll come back and do this problem. So let's talk about how spherical coordinates work. We are going to have an angle that describes the angle that a point in space makes with the positive x-axis. All right, so we're going to consider some angle coming off of the x-axis here, and that will give us some ray down here. We're also going to consider an angle away from the z-axis, so some angle coming down this way. All right, so that'll define some angle away from the z-axis like that. And then we're going to describe how far away from the origin we are, just like in polar coordinates. But we're going to be going off, so we're tilting away from the x-axis at this angle theta, the z-axis at this angle, we'll call it phi, and then the distance that we're away from the origin will be called rho. That's the Greek letter rho. And so those three parameters are going to tell us where a point is in space. So the coordinates in spherical coordinates are going to be given by rho, theta, and phi. So if I give you those three numbers, you'll know exactly what point we're talking about. All right, so what I want to do is take a moment to describe the relationship between Cartesian coordinates, the x, y, and z, and these new spherical coordinates. All right, so first of all, notice that if we were to drop a vertical line down from the point that we're at, drop a line down here, we get a right triangle. It's tilting out at us, so it's a pretty, the perspective is distorting it a little bit, but this is a right angle right down here. Okay, and so what we need to do to find the relationship is we need to figure out, what x, y, and z are. Well, to find z, we can actually draw a line parallel to this one up here, back to the z-axis, and you see I get that same right triangle up here. Okay, and now rho is the hypotenuse and phi is the angle, and the z-coordinate is just the adjacent side to that angle, right? So the z-coordinate here is going to be rho cosine phi. So there we have one of our variables. Z equals rho cosine phi. All right, well, what about our x and our y? Well, for our x and our y, we're going to have to come down here into the xy plane. So I'm going to have to drop down here. Let's figure out what this distance is. All right, well, that's the same as this distance up here. That's the opposite side to our phi. So that is rho sine phi. So that's what this distance down here is. This is rho sine phi. Okay, so now that we know that this is rho sine phi, well, now we can project another triangle to the y-axis. That makes a right angle. And we could project a line to the x-axis. That makes a right angle. Right? So we're just interested in the length of these sides of this triangle down here. Well, if this is the hypotenuse, to get my x, x is the length of the adjacent side, so it'll be this distance, the length of the hypotenuse, times the cosine of theta. So it'll be this times the cosine of theta, and that's how I get my x. X equals rho sine phi cosine theta. To get my y, y is this distance back here. That's my y-coordinate, but that's the same thing as this distance over here. That's the side opposite this angle. So that's going to be this distance times sine theta. So y equals this distance, rho sine phi, times sine theta. And these are the equations that relate spherical coordinates into Cartesian coordinates. Very useful formulas for us going forward. One more thing that we can see from this, which is worth mentioning, is this fact which will let us convert the other way. So from Cartesian to spherical a little bit. All right. So if we look at this distance here, this is rho. This is the distance that this point is from the origin. And we know how to compute a distance between a point and the origin in Cartesian coordinates. I know that the square of a distance to the origin, so that's rho squared, I compute that just by taking the sum of the squares of the Cartesian coordinates. X squared plus y squared plus z squared. You could also verify it simply by just plugging these things in for x, y, and z down here. Use a little bit of trig and you'll see that this does indeed simplify to rho squared. So this is another useful equation. Let me separate these because it's kind of going the other way. It's kind of telling you how to get, well, it is telling you how to get from Cartesian to spherical, whereas these are telling you how to get from spherical to Cartesian. But all of these are very useful equations for us. All right, so now let's talk about how we're going to be integrating. So when we integrate, we need to find the volume element. We need to think about what a little chunk of volume is going to look like when we describe it in spherical coordinates. So let's draw another coordinate system here, just to get a clean picture. The x-axis, the y-axis, and the z-axis, those are the Cartesian coordinates. It's always good to have those as a reference. And so let's pick a change in theta, a small change in theta. So we'll let's start at this angle theta and come out to, say, this angle theta. And so that change in theta we're going to call delta theta. And then we're going to think of a small change in phi. All right, so let's suppose that we started with this angle phi, and then we came down to this angle phi. So remember, this is the angle away from the z-axis, so this is our delta phi. And then suppose that we have a change in rho. All right, so we're going to start at this distance from the origin here and go to this distance. So that distance there is delta rho. We'll get to the d's later. Okay, delta rho. Let's see what we have here. I see that if I drop down away from this point here, I can come down to another point here, and if I drop down, I swing down to a point here. That might lie above this ray coming out from our first theta. If I swing back in the theta direction, swing back in this direction, I will sweep out a shape like this. So let me try to draw this in 3D if I can. So we have this wedge shape. Okay. Now, and let me just extend this down here. See what we did here. If at the bottom, its shadow down here is like this. Okay. Let me get my my face out of the way. Okay. So if we just drop this straight down vertically, it would project onto this shape, this wedge down here, which should look familiar to you. That is just like the wedge that we were looking at in polar coordinates. Okay. Now what we want to do is we want to find the volume of this piece. Okay. And the idea is it's kind of like a box, right? It's not too far away from being a box. So the volume of a box is length times width times height. All right, so let's find the length and width and height here. Well, we've got the length in this direction. Now I want to find this distance here. Well, I know that the formula for arc length tells us that if we know the radius, we just multiply that by the angle in radians to get the arc length. So that's exactly how we find this dimension right here. It's going to be the radius, which in this case is rho, and the change in the angle is delta phi. So this dimension here is delta phi. So now we have the dimension coming out this way, we have the dimension coming out this way. What we need to do is we need to get the dimension coming around this way. All right. Well, if we were to just fix the rho and the phi here and just change theta, what you'd get is you'd actually swing out a circle. If we just let theta vary but keep rho and phi fixed, we would swing out a circle over here. And that's exactly the same as the circle. We see a piece of that circle over there. So if I swung that around, I'd see I get a big circle. So really, this dimension is the same as this dimension down here. All right, so to find this, I'm going to find this. It looks a little bigger down here in my picture because I was just a little sloppy in how I drew it. But we're just looking for this. And again, this is an arc, and so we can use formula for arc length. Right? So arc length is just the radius multiplied by the angle in radians. So what we know the angle in radians is delta theta. What we need to do is we need to find the radius. We need to find the distance from here to here. Well, be a little bit careful because that's not rho. Rho is the distance going up this way. So what we really need to do is look at this triangle here, which is a right triangle. And we know that rho is the hypotenuse of that triangle. And so if I want to find the length of this side, well, let me draw another parallel line up here. That's the same thing as the length of this, right? And that is given by our angle phi, how far we've dropped down away from the z-axis, right? So that this angle here is going to be our phi, right? And the hypotenuse is the rho. And so if I want to find the length of the opposite side, it's going to be rho sine phi. So this distance here is rho sine phi. So that means this distance here is rho sine phi. Right? So that's this distance down here. Rho sine phi brings us out to there. And that's exactly what we need. We need to multiply this distance times this angle, and that will give us the arc length over here, which corresponds to the arc length that we want. So I just multiply these together. So it's rho sine phi delta theta. And that's what this is. Delta theta. Excuse my sloppy handwriting. And these are the three dimensions that we need, which give us the approximate volume of that box. All right, we call that volume. It's a small, little, tiny volume. We call that delta V. And so we see that delta V, like we said, is just the product of these three things. So it's going to be this times this. That's going to be rho squared sine phi. And then I'm going to multiply that by, these little pieces out here, the delta rho, the delta theta, and the delta phi. Now, when we do an integral, we make these volumes infinitesimally small. And so to represent that, we change the delta to a d. And so we'll write this as dv equals rho squared sine phi d rho d theta d phi. And so this is the volume element we'll be using in our integrals in spherical coordinates. All right, so back to our problem. Let's use spherical coordinates to compute this integral. So what we're doing is we're doing a triple integral over the region described there. I'll just call it R of this function dv. Now, we know what x squared plus y squared plus z squared is. We had a formula for that. Remember, that was just rho squared. And we know what dv is, right? So let's write these things down. This becomes rho squared, and dv becomes rho squared sine phi d rho d theta d phi. Now what we need to do is we need to figure out what the bounds on our integral are. Okay, so let's start writing these down. So when I put this together, I'm going to get rho to the fourth sine phi. Now let's see if we can do this in the order d rho, d theta, d phi. Let's see if this is going to work out for us. So let's see if we can figure out what phi ranges from. Let's look at this one. Well, phi, remember, is the angle from the z-axis. You can see that phi is going to go all the way from 0 out till we get to the edge of the cone, to where the cone is. Well, the cone is 45 degrees from the positive z-axis. Now, we always measure these things in radians. We'll convert this to radians. This is pi over 4. So we're actually going from 0 to pi over 4. So that is my outermost bounds. Now, what about theta? Well, theta is the angle from the x-axis. Well, you notice we go all the way around. So we're going all the way from 0 to 2 pi for theta. And rho goes from here out until we get to where the sphere is. Well, the sphere is a sphere of radius 3. So rho goes from 0 to 3. So this is how our integral is going to look in spherical coordinates. So now let's go ahead and go through and compute this. All right, so first order of business is we're going to do the innermost integral, and we are going to antidifferentiate with respect to rho. Well, that's not too bad. That is just 1/5 rho to the 5. We're going to evaluate that thing from 0 to 3, and then we'll do our theta and phi integrals. All right. So evaluating this, well, when I plug in 3 here, 3 to the 5th is 243, so it's 243 over 5. And then when I plug in 0, I get 0. So it's just 243 over 5 sine phi. Oh, I'm getting a little, I should have left a little more space here. Getting a little scrunched up. Okay, so we'll keep going here. This, you know what, I'm just going to take this whole thing and pull it outside the integral. So let's just ignore this, pretend like it's on the outside. Now we're just doing this integral with respect to theta. Well, look, this doesn't depend on theta. So it's just going to end up being, when you do this integral here, let's see if I can block that, I'm just going to get 2 pi sine phi. Right, so I'm going to have 243 over 5. I pulled that on the outside. And then I'm going to have this integral left over with respect to d phi. And then we said that that integral with respect to theta is just 2 pi sine phi. All right, well, let's pull the 2 pi outside and then just do this integral. So that when I pull the 2 pi out, I'm going to get, 486 over 5 pi. And then I'm just doing this integral here. Well, the antiderivative of sine phi is negative cosine phi. So I'm going to take negative cosine phi, evaluate it from 0 to pi over 4. Okay, well, cosine of pi over 4 is root 2 over 2. Cosine of 0 is 1. So I've got negative root 2 over 2 minus negative 1. So that's 1 minus root 2 over 2. Okay, so that's all that is. 1 minus root 2 over 2. All right, and that is our final answer. This is the exact form. Let's see, if you were to write that out as a decimal, I did this ahead of time, you get around approximately 89.4 0.44 if we round to 2 decimal places. That's the approximate value of our integral. Okay, so in this video we talked about spherical coordinates, how to express the volume element in spherical coordinates, and then how to write down an integral in terms of spherical coordinates.